Least reasonable. Well, thank you very much for the invitation to talk at this really outstanding meeting. As my title suggests, I'm going to talk about Keller cones, which were a really vital ingredient of Joe's work, which really he founded on the geometrical theory of diffraction. So this talk is in fact about the geometrical theory of diffraction. It was invented in the 1940s and 50s by Joe Keller, and it has actually been called the greatest advance in optics since Newton. But whether or not that's true, it certainly is a truly outstanding development, which is really used universally now throughout wave theory. In an interview that Joe gave, he said he began this work in the war when he was working on the submarine naval warfare. And he actually said in this interview that this theory was not immediately accepted. He said this was because the theory, in his words, was synthetic. At that time, the fashion was to work deductively from the full differential equations of motion. But as we'll see, his theory isn't really like that. But what he found was, as this theory was used in an ever greater variety of problems and gave very, very good results, it was accepted. And now it is fully accepted. If everybody can hear me, I can probably...
We're recording.
Oh, you're recording? Okay, thank you very much then. Okay, thanks. Yeah, you're welcome. So if I then talk too loud, please let me know. Thank you very much. Now, I've written there that Joe wrote a classical review paper on the subject in 1962 in the Journal of the Optical Society of America. That's often called Joe's of 62. To be precise, he also wrote another review paper in 1958. And these are two papers which are still used over and over again, and they have actually been cited several thousands of times. Now, in this particular paper, which is the one I'm going to talk about, the theory includes certain canonical diagrams which involve certain diagrams of cones, and a special case where the cone becomes flat and becomes a disk. Now, this underlying structure of a Keller cone, that's influenced innumerable applied mathematicians and physicists and engineers, including me, as we'll see. But before we proceed with the technical matter, let me just make a few reminiscences about my own personal contact with Joe Keller. Well, I first met Joe in the early 70s. This was at Woods Hole. I was a Woods Hole GFD pre-doctoral fellow. Now, when I was preparing this talk, it occurred to me that this could be true for a very large number of fluid dynamicists at DAMP and also at this meeting. There is actually a really marvelous website for this GFD program. It's got a complete set of photos going back to about 1959, I think it is, and it has a complete list of all the participants of this program and all the visiting scientists. And you will find, if you look at this website, you'll see a very, very large number of British people. Now, Joe was a regular participant in this program. He attended regularly for decades, and you'll see him in a very large number of photographs, including one only 2 or 3 years ago. So Joe was certainly attending right up to his very last years. If you look at these photos, a number of things really strike out. One is that beards come and go. Joe didn't have a beard invariably. I wrote down a few initials of DAMP members who've been there. Mike McIntyre was there, John Hinch, Mike Proctor, Paul Linden, Peter Haynes, Herbert Huppert, Nigel Weiss. I think Douglas Goff's in one of them. And even now I see that list isn't complete. I think Gray Worcester was there. Also at this meeting, Dominic Veller, I believe, were you there, Dominic, at one time? Others, Paul Della, and I think Caulfield. So a very, very large number of people would have had the opportunity to speak to Joe Keller at these meetings. And he certainly was a very influential presence. I can still remember what he talked about. He gave a presentation on smooth solutions to rough problems. And I believe that's one of his classic works, which is still referred to. At that time as well, I remember a topic that was quite recent was the Feigenbaum theory of period doubling bifurcations. And there were many discussions about this work at that time, which really was exciting. So I think through Joe's regular attendance at Woods Hole, I think he really had a great influence then over many years on many British applied mathematicians. There's also actually for this website a very interesting article by George Veronis on how Woods Hole was set up. And in those days, it seems, the men could give a commitment to attend Woods Hole regularly for many years, for several months, for every summer. So in those days, the division of sexes was such that the men, presumably, could just dump their families every year for 2 months, which of course it's a different world now. But this clearly was an important matter in setting up Woods Hole in the first place. Now, my next contact with Joe came in the early 1990s. Joe made an extended visit to Dampt. I can't remember the exact year, it might have been about 1991. And in that period, we often discussed ray theory, which then was at the centre of my work in aeroacoustics, which I'll talk about in a moment or two. If I look back now on our relations, I would say basically he took a kindly interest in my work. And in fact, we had a number of discussions. I soon found that Joe remembered pretty well everything I said, and he would often come back with a follow-up remark. And on one occasion, Joe did come back with a calculation which followed on from something that I said. So overall, I mean, Joe definitely had a profound influence on me in many ways. Well, let me now be a bit more specific in relation to what this talk is about. I'll say a few words about Joe's influence on aeroacoustics. Well, the Keller cones, which we'll see in a moment, they are now mainstream in aeroacoustic theory, and they appear either explicitly or implicitly in a very large amount of work. They appear in my own work, and when I went to Keele, I had a number of research students, Hochter and Powles, who did actually carry on with the work I started in Dampt. This was on the diffraction of sound fields by the end of an aero-engine duct, and this also leads to very interesting aspects relating to caustics, and in fact the hyperbolic umbilic catastrophe that we'll see, which does emerge very naturally from the reflected field from the end of a duct. It also relates to a leading edge noise. Keller's work on cones, it also appears implicitly in rather advanced studies, particularly carried out by Nigel Peake here at Dampt, who's worked with Kirshen in Arizona, and here in Dampt, various research students of Nigel's, Graham Keith, Rafal Assier, I think maybe here, but he's now at Manchester, Lorna Ayton, who's still here. And this work is really very sophisticated, matched expansion kind of work, but you do get very significant limits which are described in a simple way by Joe Keller's theory of diffracted rays lying on cones. In America, Amiot has been a really major influence on aeroacoustics, particularly in blade vortex interaction. A very potent source of noise is gusts or turbulence striking a leading edge, and these also produce Keller cones. And David Abrahams with David Nigro and also Rafal Assier and others, they've done very, very advanced work which does bring out Keller cones in various limits. And likewise, many other people in the aeroacoustics world use diffracted rays, for example, at ISVR in Southampton and also at Rolls-Royce and Derby. Well, let's look very briefly then at this classic paper, the 1962 JOSA paper that Joe wrote. I just scanned in my copy from an annotated version from all those years ago. Now, I'm not expecting you to read this, it's more an act of veneration. Now, Joe actually had a very distinctive writing style. He wrote short, clear sentences, and it's also very interesting that all his displayed equations, they were nearly always at the end of a sentence. Now, someone told me, I don't know if this is true, but perhaps people can confirm it. Someone told me he actually wrote his papers, but without putting the equations in initially. Then he put the equations in afterwards. So obviously, if he did this, he set up the template in a certain way. I don't know if that's apocryphal or not. But I would say that style is not so easy to imitate. And in fact, I don't write in that style myself. And in fact, not everybody likes that style. But there's no doubt about it, it's a very, very clear style. So this is the 62 paper, and what I'll now do, I'll show two diagrams from this paper, which I'm sure have influenced many, many people. This is a diagram showing the cones. Now, the essence here is that you have an incident ray coming in to the edge, which is vertical there. And if you continue that incident ray beyond the edge and then rotate it to give it every possible position around the tangent to the edge, you get a cone. And the crucial point in Joe's theory was that this cone of diffracted rays is a real object within the flow, and one can produce a theory by looking at canonical problems in the neighborhood of the vertex to get the field on these rays. Now, there is a notorious difficulty. This approach fails in certain directions, so in certain directions you have to produce a more advanced theory involving a uniform expansion. So the basic Joe Keller cone theory combined with the uniform extensions involving area functions or Fresnel functions, this is the basic theory now which many, many people use in very complicated problems. And then a special case is that the cone goes over to a flat disk, which would be appropriate in a 2D problem. Now, in this paper, the basics of the theory is given with all the basic formulae which are quoted by comparison with solutions of canonical problems, for example, by Sommerfeld type contour integral methods. Now, another diagram from this paper concerns a very, very important aspect, which is that these cones, they do actually form caustics because they touch on various envelopes. They have to interpret this diagram. This line along here, this curved line, is an edge, and there are two neighboring cones here, one cone here and one cone here. So if this edge is insonified by a plane beam, you'll see that the angles of the cones are different, and these two cones will intersect along a line that's called the caustic. Now, when you have a real problem with a real curved edge, the structure of these caustics can be really intricate. So in practice, you have to do a great deal of work sometimes to determine where these caustics are, and then put in the appropriate patching where the theory won't apply directly. You'll need an area function. But this industry has been greatly exploited and is really worthwhile in applied problems. Well, let's now see an example of that. This is my own work, which I carried out in damp. What we have here is the end of a duct, which I've idealized as being a cylindrical duct. Now, what you've actually got in the duct is a spinning mode, which you can write simply as a product of a Bessel function times the trigonometric factor. And the key point of this theory is that the mode in the duct, in fact, has a piecewise linear helical structure. But again, this is very closely related to important work of Joe's. And in 1960, there was another classic paper with Rubino in which he identified the ray structure of modes which have caustics. So even the field within the duct there is describable by a Keller theory in which gives the ray structure of a mode. Now, the crucial point here is you get these cones, one cone coming off each point on the rim, and because you know the structure of the rays in the duct, which are piecewise helices, you immediately get the cone angle. Now, if you consider all of these cones, they have a number of very striking properties. The first fact is that 1/4 of the rays on a cone actually point back into the duct. And if you just imagine that, you can see it is exactly 1/4 of the rays. So it's these rays which actually generate the reflected field. Something which isn't quite so obvious is that if you're in the forward direction, but not too close to the axis, and you consider a particular observation point, there are actually cones from rays from two different cones which strike you. And these interfere, so you get, for high frequency, you get a very striking pattern of lobes, interference lobes. But this suddenly stops, you see, when you're outside the angle of the cone. Now, when you're just to the rear of the duct, to the left there, you get at most one ray, so you don't have an interference pattern, you have a single flat lobe. And what's more, once you get beyond the angle of the cone at the left, you don't get any rays at all. So the intensity as a function of angle, it drops like a cliff. And this is exactly what happens. So these cones are very, very illuminating in giving you the entire structure of the field. I've just gone for a couple more minutes. So I've just explained there in words what I've just said. But let me just show you the acoustic structure, the field inside the duct. When you work out what the caustics do, they have this very, very complicated shape, which does actually relate closely to some problems of diffraction in the shear layer, which have been worked out by David together with Kriegsmann and Rice. But the critical point here is that as you go further into the duct, this cusp gets closer and closer to the other caustic, so that is characteristic of the hyperbolic umbilic catastrophe. And that's a 3D picture corresponding to that. I'll just flash through briefly. Graham Keith here, working under Nigel Peake's supervision, extended this to a scarf duct, which is relevant to a design of aircraft engine to make more of the sound go upwards. In blade vortex interaction, where you have gusts striking a leading edge, you can work out the cones again, and this is a diagram showing various traces of the cones on the edge itself. And I'll finish here. This is the last slide. Current work being done by Lorna Ayton here in Cambridge involves very, very advanced asymptotic analysis of gusts or sound waves striking the leading edge of a blade. You get many, many regions which Lorna is able to analyze, but the crucial point is, in certain regions, for example these outer regions, the basic field is described by the Keller kind of diffracted rays. So I'll stop there, and thank you very much. Thank you.
So, could the next speakers come and load up their talk, please? So it's Paul and Carlos. While they're doing that, if we could have a quick question for John, maybe.
Okay, well, I'm happy to sit down then. Okay, so you need to...
Thanks very much, John.
Thank you.
Need to pass over. Thanks, John, again.